Alright, welcome guys. So we have a question here. Alright, so we have a question here that says use the concept of mathematical induction to prove that this statement that we have is true for all natural numbers there. Alright, so under mathematical induction we have 3 steps. So the first step is we need to show that the statement that we have is true for n equal to 1. Then we go to the inductive hypothesis. Then we also that it is true for n equals to k plus 1, meaning that we add a new term there. Alright, so here, first step. So first step here, we say we need to show that the statement is true for n equal to 1 here. So what we do here is we get this expression that we have on the left hand side that has n in it, we equate to what we have on the right hand side here. So meaning that here we have 1 plus 2n plus 1 divided by n squared equal to n plus 1 squared like this here. So where there's n here, we're going to substitute the 1 there. So we have 1 plus 2 multiplied by 1 plus 1 divided by 1 squared equal to 1 plus 1 squared like this here. So here, 1 squared is just 1, and if you divide anything by 1, you just get the same thing that you're dividing there. Alright, then we have 1 plus 2 by 1, we get 2, plus 1 here, equal to this side we have 2 squared. So 1 plus 2, 3 plus 1, we get a 4, equal to 2 squared, we get a 4. Then here, now the left hand side is equal to the right hand side, so meaning that here we're simply going to say therefore this is true for n equal to 1. Alright, we go to step number 2, which is the inductive hypothesis. So I'm just going to erase what we have here. Alright, I'm going to erase what we have here. Like this. Alright, so we go to step number 2, which is the inductive hypothesis. So under the inductive hypothesis here, we make an assumption, or we just assume that the statement is true for n equals to k. So here we say, we assume that the statement is true for n equals to k. So what this simply means is that where there's n in this expression here, we substitute the k. So here we're going to have 1 plus 3 over 1 multiplied by 1 plus 5 over 4 multiplied by 1 plus 7 over 9, and open brackets 1 plus, where there's n now. Alright, so where there's n we substitute the k, plus 1 divided by k squared. We close here, even on this side here we have k plus 1 squared. Alright, so this is the only thing that we get to do under the inductive hypothesis. So this is our second step there. So we need to show that this statement is also true for n equals to k plus 1. Alright, so here we're just going to say third step. We need to show that the statement is true for n equals to k plus 1. So let me just erase that. For n equals to k plus 1. So what this simply means here is that to these existing terms that we have already here. We're going to add a new term now, or we're going to add a term further from the k term that we have, so that term becomes k plus 1. Okay, so mean that here we're going to have 1 plus 3 over 2, or 3 over 1 rather, 1 plus 5 over 4, 1 plus 7 over 9, then 1 plus 2k plus 1 divided by k squared. So this is the k term that we have here. So now, since we're talking of the term which is the k plus 1 term there, so it simply means that if this is k here, then the next term is going to be the k plus 1 term. So here we say 1 plus 2, where there's n we substitute k plus 1 plus 1 divided by k plus 1 squared, we equate it to, now on the right hand side, where there's n in this expression here, we substitute with k plus 1. So here we're going to have k plus 1 plus 1 squared, like that. Now, when you look at these terms here, starting from the first term all the way up to the k term here, you notice to say that these here, they give us this inductive hypothesis that we have here, or they give us the left hand side of the inductive hypothesis. So what do we need to do here? Where there are these terms here, we can just substitute with the right hand side of the inductive hypothesis there, please. Alright, so here we're going to have k plus 1 squared multiplied by, so here we have 1 plus, so 2 by k here, we get 2, k plus, so 2 by 1 we get a 2 plus 1, that's going to be 3, divided by k plus 1 squared equal to, then here k plus 1 are going to get a 2, so we're going to have k plus 2 squared here. Now, our goal here is to show that the left hand side is equal to the right hand side. If we're able to show that, then the statement that we have is true under mathematical induction there. Okay. So let's simplify this a bit here. So here, we're going to make what's inside these brackets here a single fraction. So here we have k squared, or k plus 1 squared, open brackets. Then the common denominator here is k plus 1 squared, like this. Then this is the same as over 1. 1 into this, we get 1 multiplied by the k plus 1 squared there. So let me just erase this. Okay, so here we're going to have 1 into this, we get k plus 1 squared, by 1 we get k plus 1 squared, plus k plus 1 squared into k plus 1 squared was just simply going to get 1 multiplied by that, we get 2k plus 3 equal to k plus 2 squared, like this. Now, since these two terms are multiplying here, this term and that term can simply cancel out there, so leaving us with, so let me go to the next bit. Okay, so leaving us with k plus 1 squared plus 2k plus 3 equal to k plus 2 squared, like this. Now, if we expand what we have here, so I'll do this on the next page. Right, there's still space. Okay, so if I expand this here, you'll notice that that's going to be k squared plus 2k plus 1 plus 2k plus 3 equal to, if we expand what we have this side, we're simply going to have k squared plus 2k plus 2k plus 4. So then if we add everything that we have this side, we're going to have k squared plus 2k and 2k we get 4k, 1 plus 3 we get plus 4, then this side as well we're going to have k squared plus 4k plus 4, like this. We've shown to say that the left hand side is equal to the right hand side, so therefore this here is true for n equals to k plus 1. So if this is true for n equals to k plus 1, you can just conclude by writing to say that the statement that we have is true under mathematical induction for all natural numbers there. Alright, thank you.